Have you ever just stared at a screen full of code and wondered what it's actually doing? Ward Cunningham once said, if you don't think carefully, you might believe that programming is just typing statements in a programming language. And honestly, that really hits the nail on the head, doesn't it? Real programming, especially when we're talking about data science, isn't just about memorizing syntax or frantically typing out commands. It's fundamentally about how we structure, how we understand, and how we manipulate data to pull out those truly meaningful insights. So welcome to today's Explainer. We're dedicating this chapter to completely demystifying data handling in Python. Specifically, we're focusing on a literal powerhouse in the data analysis world, the PANDAS library. Seriously, whether you're dealing with messy spreadsheets, complex databases, or just endless logs of data, PANDAS is absolutely going to be your best friend. We're going to break down the core concepts from the chapter visually so you can finally stop wrestling with your data and start actually understanding it. All right, here's our roadmap for the chapter. First, we'll meet the Python libraries. Second, we'll compare Pandas versus NumPy. Third, we'll uncover the power of series. Fourth, we'll be diving right into data frames. And fifth, we'll wrap up by working with CSV files. Okay, let's jump right into section 1. Meet the Python libraries. Well, before we can build our data house, we really need to know what tools are sitting in our toolbox. In Python's scientific ecosystem, we have what we often call the big three. First up is NumPy, which stands for Numerical Python. It's incredibly fast and purpose-built for heavy numerical array operations. Then we have Pandas, short for panel data. This is our high-level data manipulation tool. And finally, there's Matplotlib, which is your go-to for turning all those raw numbers into beautiful publication-quality visual plots. You can kind of think of Pandas as your central command center, right? It's actually built straight on top of NumPy, and it integrates absolutely perfectly with Matplotlib. Moving right along to section 2, Pandas versus NumPy. Now, a super common question people ask is, hey, if we already have NumPy for number crunching, why do we even need Pandas? And the answer really just boils down to flexibility. You see, NumPy requires homogeneous data. That means everything inside a NumPy array basically has to be the exact same type, like all numbers. And it relies on a strict integer index that always starts at 0. But as we all know, real-world data is messy. It is completely heterogeneous. A Pandas data frame, on the other hand, can hold a wild mix of floats, integers, and strings all at once, beautifully organized in a tabular format. And best of all, it allows for labeled custom indexes. So you can literally call a row sales instead of having to remember that it's, row number 4. Which brings us to section 3, the power of series. So, how exactly does Pandas construct these magical tables? Well, it starts with the absolute simplest building block, which is called a series. A series is simply a one-dimensional array that contains a sequence of values. And the cool part, it can be absolutely any data type. But here is the real secret sauce. Every single value has a data label attached to it, which we call its index. If you're trying to picture it in your head, just think of a series as a single, standalone column pulled straight out of a standard spreadsheet, complete with those row headers on the left side. Now, once you have a series, you obviously need to know how to get your data out of it. We basically have two main ways to access these elements. First is positional indexing. This uses standard integers starting from 0, just like a standard Python list. But, and this is a major trap, so listen closely, when you slice a series using positional indexing, it actually excludes the end value. On the flip side, we have labeled indexing, which uses those awesome custom labels we just talked about. When you slice using labels, it includes the end value. Seriously, keeping that one little distinction straight will save you hours of debugging later on. To really understand what you're working with, Pandas provides some incredibly handy attributes. Instead of writing out complex loops to analyze your series, you literally just append these little tags to your series name. Need to know exactly how many elements are hiding in your data? Just slap on a .size. Want to double check if your data import actually worked or if it just pulled a blank? Use .empty. These attributes basically give you instant X-ray vision right into your data structures. Now take a look at what happens when we actually try to do math with a series. Let's say you want to add series A and series B together. Pandas is smart, right? It automatically matches them up by their index label, so A pairs with A, B pairs with B, and so on. But look closely at row B here. Series B is completely missing a value there. By default, Pandas kind of panics and throws a nan, which stands for not a number, straight into your results. But, as you can see on the far right, if you explicitly tell Pandas to use fill value equals 0, it seamlessly replaces that missing data with a 0. It saves your math operation and keeps the whole dataset remarkably clean. Let's move on to section 4, diving into data frames. Okay, so how does this whole thing build from a simple one-dimensional column into a fully functional two-dimensional structure? Well, if a series is a single column, a data frame is the whole shebang. It's the entire spreadsheet. It is a two-dimensional labeled data structure containing rows and columns. And because it's essentially just a collection of series mashed together, each column can have a totally different data type. This right here is the core object you're going to be using like 90% of the time in Pandas. It's basically the Python equivalent of a complete, robust database table. So the absolutely crucial point here is how we actually pull specific data out of this massive 2D grid. We get to upgrade our toolkit for this. We use the .locRow method for label-based indexing, which lets us pinpoint exactly which row and column labels we want to grab. But even more powerfully, we get something called Boolean indexing. This allows us to select subsets of data based on the actual values inside the data frame, rather than just relying on where they happen to be located. Let me show you what I mean. Imagine we have a data frame called result.df that contains a bunch of student test scores. By typing out a simple yet incredibly powerful line of logic like result.df.lock maths greater than 90, Pandas will literally sweep through the entire maths row and evaluate every single score. It returns a true if the score is greater than 90 and a false if it isn't. So boom, you can instantly filter out your top performing students with just a single line of logic. It's a real game changer. And just like we saw with series, data frames have their own attributes to help you understand their layout. Let's say you've just loaded up a massive complex report on forest area spanning a bunch of different states. Before you even start analyzing, you want to see what you're dealing with, right? Well, calling .index will immediately spit out your row labels, showing you categories like geoarea or very dense forest. Meanwhile, calling .columns reveals your data points, showing you the specific states being tracked, like Assam, Kerala, or Delhi. It's your super fast structural overview. Finally, let's wrap things up with section 5, working with CSV files. Because, let's be honest, all these fancy data frames aren't really very useful if they only exist in theory. It brings up the ultimate practical question of the chapter. How do we actually get real-world data, stuff from your boss, a random website, or some legacy database, into Pandas so we can finally get to work? The answer, almost universally, is the good old CSV file. A comma-separated value file is exactly what it sounds like. It's just a plain text file where every single line is a row and every column value is separated by a comma. It is literally the universal language of data. Every single spreadsheet software out there, from Excel to Google Sheets, can easily export to CSV, making it the absolute perfect bridge right into Python. And here is the basic 3-step workflow that you'll be using on nearly every single data science project from here on out. Step 1, you import your messy data file into a pristine Pandas data frame using the pd.readcsv function. Step 2, you use all the amazing tools we just talked about, the series slicing, the Boolean filtering, the math operations, to analyze and clean up that tabular data. And step 3, once you've extracted your golden insights, you push that data frame right back out into a brand new file using 2CSV, all ready to be shared with the world. So you've seen how we scale all the way up from simple arrays to labeled series, and finally to these incredibly powerful two-dimensional data frames that interact perfectly with real-world CSV files. Now that you've got the structured knowledge from this explainer to actually handle, slice, and manipulate data effortlessly, what real-world problem are you going to solve first? Thanks for joining me today. Stay focused and keep learning.